Let's start. So, yeah, before continuing with the discussion on SAR, let me just clarify something basic. So, found this in one of the answer sheets, so wanted to clarify. So, say you have voltage source, say you have a capacitor, and then you basically connect it. Let us say this is some VREF, and see what will be the charge that the voltage source provides to the capacitor. Is that okay? I mean, the capacitor is, let's say, initially uncharged, zero charge. Finally, it charges to C times VREF. That charge of C VREF is coming from the voltage source. So, which means what is the energy delivered by the voltage source? C VREF square. We discussed in the class. Now, what is the energy stored in the capacitor? So that should ask the question, right? Where did the remaining half C VREF square go? But it's an ideal switch, right? What happens? So it will be impulse, correct. I mean, if it's an ideal switch, it's going to be an impulsive current. So
Different of radiation or something like I forgot that.
okay, so let's. I mean, in a practical case, what will happen? Let us say it has a on resistance. How will the current look like? Let's say it's R on. It will spike up to V in by R on and V ref by R on. It will decay like this. So if in this case, how is the energy dissipated? In the resistor, but in which format? Electrical energy is converted to which? Heat energy. It's dissipated in the form of heat, right? Now, let's say in practice you have a very good switch that's a very small on resistance, right? So if you turn on the switch instantly, what do you think might happen? It's not an ideal case. Let's say it's a practical scenario where you have a really small on resistance. You turn on a switch. I mean, you might have observed in practice, right? Let's say you have a very high voltage signal. You have a very good switch. You switch it on instantly. You'll see a spark, right? So that's how that energy is getting dissipated there. And here, I mean, like some of you had hypothesized, if it's an ideal switch, it's an impulsive current. So what will happen is the energy will get, I mean, the energy will get radiated in other format. How will it get radiated? I mean, that I let you guys think and figure out, right? But the deal is this, right? The energy stored is half CV square, but the actual energy that you are taking from the voltage source is twice that. Okay. Cool. Let's then move on. So in the last class, we started to look at some of the non-idealities we might encounter in SAR, and the first thing we saw was incomplete settling of the DAC. And we decided to tackle by introducing redundancy. The idea is you go and do comparisons once again to correct for any errors that you would have made, right? And in general, you can make this error due to multiple reasons. Let's say it is due to incomplete settling of the DAC. Let's say any noise in the comparator. Because of any reason, if you make an error, if you have a redundancy, you can go and correct for it later, right? And if you are dealing with DAC settling, the maximum error can occur in the initial phases, because in the initial cycles is when the DAC has to charge from 0 to VREF by 2, right? Because in the initial phase, the jump is the maximum. So there is more chance that you might make an error during the initial phases. So you try to have redundancy for the first few comparison steps usually, right? Great. Now, I mean, if you have a redundant SAR, if you have an n-bit SAR, how many comparisons I will be making? If you have a redundancy, how many comparisons I will make? At least more than n, right? So it will be greater than or equal to n plus 1. So at least, I mean, now at least looks like I'm making more comparisons, so I'll be taking more time. Isn't it? But if you actually think about it, since we have redundancy, we know that if we make an error, we can correct for it, right? So which means the moment I have redundancy, I don't need to wait for the DAC to settle fully. So I don't need to give enough time for the capacitor voltages to settle. I can shorten that time and then do the comparison. So even if I make an error, I can correct for it, right? So that way you don't have to spend enough time for the capacitor voltages to settle. You can shorten those times. So even though you do n+1 comparison or n+2 comparison, the overall time can be same as the time in a usual n-bit SAR, and or sometimes you can make it even shorter than the usual. So that's the deal there. Okay, so today let's continue with a few other issues that you might face in a SAR, and we'll see how we can tackle. I mean, one reason I want to discuss, I mean, we'll be discussing quite a few of them. One reason I want to discuss is, see, I not only I want you to guys understand the bottlenecks in a modern SAR ADC design, but in general at the end of the day, what I want you to take back home is this, right? You should try to get a feel for the basic premise of the problem and the general principles behind the problems, the solutions that we come up, right? Because the moment you have this top level understanding, you'll be able to relate the same problems to the problems you'll face in other circuit design or in any other engineering problem, right? So the moment you make those comparisons, the same principles you can use to come up with solutions there. That's the whole point, right? I mean, in general, that's how you are supposed to learn anything, right? It is not just learning a particular subject, particular area. Of course, you should develop, like subject domain knowledge if you want to specialize in that. But what will help at the end is to get a basic top level understanding and your ability to expand what you learned to solve other problems. So at the end of the day, I'm not expecting guys to remember all the solutions, right? What I expect you to is to develop the ability of problem solving. Given you know how to solve some problem, how can you extend the same to solve maybe a similar problem in a different domain? That's what makes a good engineer, right? So okay, let's go on. So yeah, the first problem, the second problem that we can face in SAR is this, or it's not a problem by the way. So I mean, we know that we implement SAR in an asynchronous fashion. We saw in the last class, and if you recollect, the way we do the asynchronous SAR or the sequence of operations we do is this. First we do the comparison. Once comparison is over, we generate the valid signal. After doing the first comparison, what do we do next? After we finish making the first comparison, we have to remember that the result of the comparison has to be stored, right? And for that, we store it in a D flip-flop. Input is ready for the D flip-flop. What is the other thing that is required? Clock, right? So we generated the clocks. So we generate, let us say, the clock 5K, and then you go and store the data decay. And then what do you do next? We'll do the reset, but I mean, before that, should we do something also? I mean, this is first comparison is done. I've stored the result of the first comparison.
Then I go back and just change the switches and according.
I have to generate the next reference voltage, so I have to go and switch the capacitor, right? That's the next step I have to do. I'll just write switch the capacitor. I'll have to do this to generate the next set of reference voltages to compare, and then I'll do this in a loop, right? Now this works perfectly fine, and this is how most of the SAR ADCs are designed. But now let us say you are trying to design a very high speed SAR ADC, right? So which means I am trying to minimize the delay in this overall operation. Okay? So let's actually try to look at each of these operations and see which of these are absolutely critical and which of the operations are not so essential, and let's see if we can do something there. Let's start with the first one, comparison. Do you think we have to do this comparison? That's definitely needed. If the comparator takes so much time, we'll have to wait so much time. What about this guy switching the capacitor? That is essential to generate the set of reference voltages. We can't do anything. Why are we doing this operation? Yeah, but why are we even doing it? If we don't do it, what will happen?
You will lose the information.
Because the reason we are doing this is because we are using a single comparator to do all the n comparisons. So which means if I finish making the first comparison, I should store the data, right? Else the comparator is giving the next bit. So if you think about it at the top level, the fundamental operation is not this. The two main operations in a SAR are these, right? You compare, generate the next reference, and keep doing it. The reason we are doing these two operations is because the way we are implementing and the way we have implemented is we are using a single comparator to do all the n comparisons. So which means I have to go and store the result of every comparison every time. So this looks like it is not absolutely critical, right? So let us say I want to get away with this delay. I don't want to do this. So how can I not do this? What should I do? Exactly, and not alternatively, but that's the point, right? Here we are basically doing this because we are using the same comparator for all the n comparisons. If I don't want to do this step, for doing n comparisons, how many comparators I should use? N comparators, right? Every comparison I will do using separate comparator. Then I don't have to go and store the data locally. I mean store the data in a separate place. The comparator itself will be storing the data, right? So that gives rise to this thing. So there is no change in the capacitor switching scheme. It is all the same old. So we'll have the positive side, negative side. The only difference is instead of having one comparator, I'll have n comparators. So let's say this is the second comparator. Nth comparator. The same inputs go for all the comparators. So now let us say this is the sampling clock 5s. So first we sample the input, you guys know that. So when can I start the first comparison? When the sampling clock goes slow is when I can start the first comparison. So I can use this guy to trigger the first comparator.
It fires and doesn't have 50% unit.
Yeah, doesn't have, right? It should not have. Yeah. So we can use this clock to trigger the first comparator to make the first comparison. Once the first comparator has finished its job, it is going to generate the valid signal. Then what can I do next? Once the first comparison is done, what will I do now? I'll basically go and get ready for the next comparison by switching the capacitor here, and the next comparison will be done by the second comparator. So I'll use this valid 1 to trigger the second comparator to do the second comparison. So basically once the valid signal goes high, I go and reset this comparator and parallelly switch the capacitors, right? And then start the second comparison. So this way I don't have to do this additional task of generating a clock 5k, storing the data decay.
Will I not lose the information from the first?
No, right? Because if you think about it, the comparator is going to store the data. I mean, if you see the comparator, if you remember, we had a strong arm latch or whatever, followed by an SR latch, isn't it? So SR latch is going to store it. The data is stored locally in each comparator now. Earlier we couldn't do that.
Taken by a comparator will change after this reference voltage is changed.
So once the SR latch has, no, that will not happen. You think about it. But even if that will happen, you can do something. But the point is, you can disable the comparator or something. But I'm just giving the basic principle, right? The idea is if you have n comparators, you don't have to do this additional job of generating a clock, storing it. Because the storing inherently happened in the comparator itself, locally. So now once the second comparator is done, it will generate a second valid. You start it for third, and then you can do this. Okay. So this is called as loop-unrolled SAR. So I mean, we can ask. I mean, is this really critical? This delay, is it so much? But in normal cases, no. But let us say you want to realize a really high-speed ADC, right? And in particular, let's say you want to realize a gigasamples per second ADC for serial links. There, as we saw, we have time interleaving, and usually time interleaved SAR ADCs. And at those high speeds, even if you say a few hundreds of femtoseconds of delay, that's going to be a big deal, So in all these time-interleaved SAR ADCs for gigasamples per second applications, we usually do it in this loop-unrolled manner. So here for an n-bit SAR, how many comparators I need? N comparators. If I were to have it as a flash ADC, how many comparators I would have needed? 2 power n minus 1. So it's definitely much better. Right? But now I am using more than one comparator, that is I am having a total of n comparators here. So do you foresee any other issue if I have multiple comparators?
They are not equal. Mismatch.
The offset, as we saw in the flash ADC also, each comparator will have its own offset and it's going to be different for each comparator. So what is the implication of the offset? No. Each comparator is going to have different offset. How does it impact the overall ADC performance? I mean, let us say if there is no offset, right? If I were to plot the input-output characteristic of the ADC, how will it look like? It will be an ideal staircase. So now if each comparator has different offset, what will happen? Yeah, it will basically be distorted. So what will happen? It will introduce non-linearity. Okay. So now we can't tolerate any offsets in these comparators. So you have to go and correct for it. And as we discussed during the comparator time itself, this is usually done in the digital domain through some form of digital calibration. So this is something that you have to do here. Okay. Cool. So yeah, take away from this life lesson, time is really valuable. Don't waste your time doing unnecessary stuff. Optimize your time properly. So next time if you watch a Netflix series, it's okay to watch one episode. So the moment you are trying to click play next episode, think twice, right? Okay, anyways, let's proceed. So this is one of the modifications you can do to SAR to improve the speed. Now, the third issue, or the other issue that you can encounter in SAR is this. Now, in a SAR, if you have an n-bit SAR, right? How will be the capacitors arranged? I mean, I'll have lowest capacitor is C, that is always connected to Vref, and then how will be the capacitors? I'll have C to C, and then till what? Let's say I have so much.
Power n minus 2.
No, what will be the
Power n minus 2.
n minus 1? I mean, think about it, right? I mean, I need to have n capacitors for switching.
Yeah.
This is C, nth capacitor will be n minus 1. So which means the total capacitor I have is what? What is the total capacitance I have? 2 power n. Right? Now you remember when we are sampling the signal is sampled onto this entire capacitive array. Right? So just during sampling I can think of the scenario like this. I have the sampling switch and it is sampled onto this entire sampling capacitor. I'll actually call this as CU, U standing for unit capacitor. And the total sampling capacitance I have is 2 power n times CU. Okay. Now, when we are designing a sampling circuit, how do we choose the value of the sampling capacitor? What determines the value of the sampling capacitor? KT by C noise, right? So we choose the capacitance value based on KT by CS requirement. Let's do some quick calculations. So let us say I am designing a 10-bit SAR. What is the maximum sinusoidal signal to noise ratio I can achieve here? Yeah, 60 dB roughly, 6n, right? Roughly 60 dB, just it's enough. Now let us say my maximum signal amplitude is like this, minus 1 volt to plus 1 volt. What is the signal power? Half. So in decibels, how many decibels is it? Minus 3 dB. So what should be the noise power? Minus 63 dB. So in absolute scale, this is 10 power how much? I mean, I'm not asking the number, right? Minus 63 dB. 10 power minus 6.3. So many volt square, whatever. Okay. Now I want this KT by CS to be equal to 6.3. Let's do a rough calculation. So this has to be KT. K is Boltzmann constant. T is temperature in Kelvin. We'll look at room temperature. 6.3. Again, let's all do a back of the hand calculation, right? Let's say this is 10 power minus 23. This is 100. It's 10 power minus 6. Huh? Yeah, that's what. How much is it? 14 or no, it should be 15, right? 10 power minus 15, right? So this is around 1 femtofarad, roughly, right? So to get a 10-bit resolution, it is more than enough if I use a sampling capacitor of 1 femtofarad, right? But in a SAR ADC, the sampling capacitor is 2 power n times the unit capacitor you will need. So this is going to be 2 power n, n is 10. So what is Cu roughly? How much is 2 power 10? 1000, right? I mean it's kilo. So this is no, pico is higher. 10 power minus 18, right? That is attofarad. Okay. So now you see that the minimum capacitance I need to have is 1 attofarad, and that's actually really small. Yeah, we can't, basically turns out we can't realize such small capacitors reliably on chip. So given a technology, you will find that the minimum capacitance you can realize reliably on chip will be something. Let me call that Cu minimum. So unit capacitance cannot be smaller than this guy. So basically what you will have to do is you choose your sampling capacitance to be 2 power n times the Cu min. Now let us say it turns out you can only realize a minimum capacitance of 1 femtofarad, right? So what will be the sampling capacitance? 1 picofarad, right? So you see that ideally thermodynamics says you can use 1 femtofarad of capacitor to meet your signal to noise ratio, but because of the fact that the minimum capacitance I need is so small, I end up using a much larger capacitor which is 3 orders of magnitude larger, right? And this is simply happening because if you think technology constraint and the way we are making the SAR, right? If it was a normal ADC, it is okay. If it was a normal ADC, I can put a 1 femtofarad, I am good. Because in a SAR, the minimum capacitance to maximum capacitance, that spread is so high, right? I have a C total, but the maximum to minimum capacitance ratio is so high. So this is the problem, right? So let's see if we can do something about it. And for that, let's look at a 6-bit SAR. If you have a 6-bit SAR, how will the capacitors, what will be the maximum capacitor I will have? 32C, 2 power 5, 32C. And the next, let's all write it. This is 16C, 8C, 4C. And then you will have 1C connected to VREF all the time. Fine. Great. And the total capacitance is 64C, right? Now let us say I want to limit the maximum capacitance I have to be 4C. Let's say I say that. If this were to be the case, what should be the next capacitance value? It should all scale by 2. So this should be 2C, C. This should be? No. C by 2, right? We are scaling in a binary weighted fashion. C by 4, C by 8 and C by 8. Is that okay? But now the technology constraint says you can't realize anything less than C, let us say. So this is something I cannot do now. Okay? Yeah, it's not that good, because if you put capacitors in series so many times, let us say if you want to get C by 8, you have to put 8 capacitors in series, right? So it turns out each capacitor will have top and bottom plate capacitors, parasitics, so that will limit it. So that's a good suggestion, but it is not so practical actually. If it was just C by 2, we can do. But let's say, I mean, this I gave a 6-bit SAR, right? Let's say you want to make a 10-bit SAR. You want to get C by, let us say, 256. Putting 256 of them is not going to be practical. Now let us say I take a 3-bit SAR. What will be the maximum capacitance I have? 4C. So you all 4C, 4 saw that. 2C, C, and C connected to VREF. Right? Now let us say I have, okay, let me just copy this. Let's say I have one more 3-bit DAC. Now I have two 3-bit DACs. What is the natural question you can ask? I started with the goal of making a 6-bit SAR using a 6-bit DAC. Now I have two 3-bit DACs. What could be the natural question you will ask? Can I combine these two, right? And you can see, right, this portion is basically now a 3-bit SAR, right? 4C, 2C, C. Now the question to ask is, instead of doing this guy, can I use this? Okay, so let's see if that is even logically possible. So let me actually erase these. Okay, I'll have to push this up. Great. So the first portion is fine. This is a 3-bit portion. This portion we are saying if you can replace it with this guy. Now actually if I look at here, right, what is the total capacitance I see? 1/8 plus 1/8, 1/4. 1/4, 1/4 is 1/2. C. The total capacitance I see to the right of my first 3-bit DAC is C. Right? Whereas what is the total capacitance here? 8C. So I can't simply go and put it here, right? So let's see if what can be done. Let me actually erase this. So I'll erase. But I don't want to use this. I somehow want to use these two guys together, right? But I can't go and simply connect this because now I see that the total capacitance here is 8C. But in the original case, I wanted a capacitance of C. So now think about this. I have a total capacitance of 8C looking down. I want to connect this point to this point. But the total capacitance looking here must be C. So I can't connect this directly. So what can I put in between? I have a total capacitance of 8C. But before, I want to make sure that total capacitance looking is much smaller, C. I can put another capacitor in series, so that series combination becomes equal to C, right? So what I can do is the following. I'll put something like this. Okay. Let's say this is Cx. Now let's see what is the value of Cx, right? So the series combination is Cx. Remember, this is 8C. 8C by, this should be equal to C. So what do you get for Cx? 8/7 of C is what? So basically if you take a capacitor with this value and put it, so looking to the right of it, it looks like it was same as before. And even these guys are binary scaled, so it will actually match what you had earlier. Okay. So you can also quickly confirm that also. So what we'll do is this. So what our claim is this, right? This portion, let me copy this. We are claiming that this portion behaves in the same fashion as having capacitors like this, C/2, C/4, C/8 and so on. That is our claim. So let's see if it's correct. So let's say I go and connect the voltage source across this branch. Let's say it's some V. What are the charges stored in the capacitors? In the C/2 capacitor, what is the charge stored? CV/2, CV/4 here, let's look at the charges stored in these capacitors, and if they are equal, then we have done the same job. Okay. So let's do the same. So I'll do the same experiment. I'll go and connect across it like this. This is the same voltage V. What is the total capacitance looking here? C. That's what we started off with. So what is the total charge the voltage source is providing? CV. So the charge that flows here is C times V. Now this charge of C times V flows through a series combination of Cx and Hc. What can you say about the charges stored in the two capacitors? I have a charge of CV flowing into two elements in series. The charge stored will be same, right? So the charge stored in this entire Hc capacitance is CV. So now the goal is to find charge stored in each capacitor. I have a total charge of C times V. That is going to get split into these 4, right?
4 by 8.
So it's going to be 4 by 8. 4C by total is Hc, that is CV by 2. Similarly, here you will get CV by 4.
That is obvious, right? We started with that, it should be same.
Yeah, just confirming it, right? I mean, you can also think of it like you can also find, right? If you're not comfortable with charge, you can find voltages. If this is V, you can find what is this voltage, capacitive division, and then that voltage times 4C will give this. You can work it out. The bottom line is, I can, instead of using these ones where I had to use small capacitors, I can instead use this arrangement. I mean, if you are not still convinced, you can go and work out what are the voltages when we switch each capacitor to ground. I'll give that as an exercise so that you will find that this is indeed working as a 6-bit SAR, generating the required reference voltages. So now we know that this guy is going to realize a 6-bit SAR, and we have done that by taking two 3-bit DACs and kind of putting them in series. Right? And this capacitor is often called the bridge capacitor. And this technique in general is often referred to as, I'll write it here, split C-DAC. Basically, the 6-bit DAC is split into two 3-bit, and then you are connecting the two 3-bit DACs. So now we can generalize it. Let us say now I have an N1 bit DAC here and an N2 bit DAC. In principle, I should be able to connect these two and realize an N1 plus N2 bit DAC to be used in a SAR, right? And I'll have to put a bridge capacitor here. Oops. Now when I had a 3-bit DAC here, the capacitor I used was 8 by 7C. Now I have an N2 bit DAC. What do you think the value of this must be? 2 power? No, it's not n by 2, right? We had a 3-bit here. 3-bit gave 8 by 7. Okay, it was 2 power n2. Yeah, okay. 2 power n2. This should be the capacitance value. And this guy goes to the comparator as usual. No other change. So this is also commonly done. Oops. Okay. Have to close this. Okay, the thing is gone, but let me just write. So I have N1 bit. So I have N2 bit. So we'll go to the capacitor. This is 2 power N2. And this goes to the counter. So this technique works, but one minor issue with this is the bridge capacitor value, you see it's not an integer, right? It's 8/7 of the unit capacitor. In general, if you have a capacitor of C, you can realize an integer multiple of the capacitance. I mean, if you have C, how do you realize n times C? Huh? You put n of them in parallel, that gives n times C. That's how you realize. But now you see you have a fractional capacitance, that becomes tricky to realize. That's one issue with this. And with this technique, at least it looks like on paper I have reduced the effective sampling capacitor, right? So here in the 3-bit plus 3-bit case, what is the total sampling capacitance I'll have now? 4C, 2C, C and C. 8C. But if I were to use a regular 6-bit SAR, what would have been my sampling capacitance? 64C, right? So I basically reduce the total sampling capacitance significantly. So with this, at least on paper, it looks like I will be able to use a sampling capacitor as dictated by KT by C, right? But in practice, there is one other constraint that will limit the capacitance value, which is what we look next. Now again, in a SAR, we have capacitors arranged like this: 2C, 2C, 4C and so on, right? Now if I have a capacitance of C, as we just saw, to realize a capacitance of 2C, I'll put two of them in parallel. But by this time you guys know that no two things are exactly identical, right? So there is going to be mismatch among each of the capacitors. So this first of all, this itself need not be the same capacitance that you realized. But let us say this is some C hat. If at least this were 2 C hat, it is okay. But this will be some 2 C hat plus delta C and so on. So ideally, let us say you had capacitors arranged like this: 8, 4, 2 and 1. Now the scaling factors will be, let us say, 8.001, 3.998, something like this. Simply because there is going to be mismatch among the capacitors, right? So let us say we have mismatch among the capacitors, the weighting factors have become like this. Now what will be the impact of this on the overall ADC performance? Okay, so first you should ask the question, right? Why did we even have capacitors arranged in a binary weighted fashion? We have to generate reference voltages. It was derived by 2, derived by 4. It was all binary scaled, and that is why we want to keep the capacitors also in a binary scale fashion. But now I am saying the scaling factors are not going to be same. So if ideally you wanted something like this, where these are the reference voltages, now they are going to be different. So what will happen now? It will again result in nonlinearity. So this is going to be a huge problem, which is the mismatch in the capacitors. So if you have any mismatch, you see that it is straight away going to result in nonlinearity, right? So from usually what will happen is, from your linearity specification, from your signal to noise and distortion ratio you want, you will find what is the amount of mismatch you can tolerate. And again, remember, this mismatch is a random phenomenon. So to quantize it or to quantify this, we use statistical measures. So we deal with standard deviation. So we usually say sigma of delta C by C, that is a relative mismatch I'll take, normalize it to the capacitance value, and I'll take the standard deviation of this. So from the linearity specification, you will find you required some value of this standard deviation. And it turns out, just like as we saw for mismatch in transistors, if you want to reduce the mismatch, what was one simple thing you can do? You can increase the size, and the reason was the mismatches were all inversely proportional to square root of the area. Okay, so even in capacitors, the same thing holds good. So standard deviation of the mismatch is inversely proportional to the area. So which means to meet a particular matching condition, you will end up having a minimum area for the capacitors. Fine. So since you are going to have a minimum area, that straight away sets your minimum capacitance you can have. because to have a good matching among the capacitors, it turns out that we have to use some specific minimum value at least to guarantee matching, right? So in more often than not, in practice in SAR ADC, the unit capacitor is always decided by the minimum capacitance you can have to get a particular matching. So now this will be your unit capacitance. It should be at least greater than or equal to this. So your total sampling capacitance will be 2 power n times this guy. So once again in practice you will find that you will not be able to design the sampling capacitor so that you meet the kT by C noise. You will end up over designing it simply because you want to get good matching between the capacitors. Okay. And the practical number to get for this standard deviation is around 0.1%. This is something achievable in CMOS process. If you want to get anything smaller than that, it is not practical. And it actually can work out that if you can get a matching of around 0.1%, with this matching you can realize around 10 to 12 bits of resolution without taking a hit on the linearity. I mean, for 10 bits, what should be the signal to noise ratio? 60 dB. So basically 60 to 72 dB of SNDR you can achieve if you have this kind of. So if you want to get a higher resolution, you have to go and correct for this mismatch. And in practice, people have realized, let's say 15 or even 16 bits are. But in that case, you have to go and do something to correct for this mismatch. And remember, we have a mixed signal system now. We have both analog and digital. Now, if you want to correct for this mismatch, broadly, how many ways in which I can do this? I want to correct for the mismatch. It's a mixed signal circuit. So, in basically 2 ways, I can either correct in the analog or I can correct in the digital domain. Which one do you think we prefer? Digital, because that's more flexible, and in practice that is what is done. We do some kind of digital calibration to correct for the mismatch. So I'll give a quick flavor of that, or I'll at least explain how can you even correct for this in digital domain, right? And for that, let me try to show the block diagram that we had for SAR. So the SAR can be modeled like this, right? You had one comparator, you had the input, and the input is compared with a bunch of reference voltages. And what determines what reference voltage you compare the input with? I mean, here I'm going to have a bunch of reference voltages, right? Yeah. But what decides what is the reference voltage I'll be using? The previous comparison is going to dictate it. So inherently we saw there is a feedback. So let's say this is the digital output. So here we have some arrangement that goes and generates a reference and we feed it. Now let us say we have the SAR ADC comparing the input in this range minus Vref to plus Vref. What is the first reference voltage I'll compare my input with? 0, right? So the feedback signal first will be 0, right? Now the way you can interpret this is like this, right? So this is a negative feedback system. So as of now, from the information the system has, which is the fact that the input lies in this range, what it has done is it has approximated the input as 0, which is basically the middle in this reference. Now let us say you get an additional information now. You find that the input is greater than 0, so it is lying in this range. What will be the reference voltage I will compare my input with next? Vref by 2. So next the SAR will compare with, let me write it here, Vref by 2. So this voltage will change to, now again you can interpret it like this, right? Now the loop has got the information that the input is lying here. So it is approximating the input as Vref by 2, and that is why the feedback signal is Vref by 2. Right? Now let us say here I find the input is smaller than Vref by 2. Input is in this range. What will I compare my input with? Vref by 4, right? This 1/4 L, right? So this will become Vref by 4. So again, the way to interpret it like this, right? With the information available now, the negative feedback loop has approximated the input as Vref by 4. Right? So if you keep doing this for more and more cycles, you will get a better and better approximation for your input signal. And if you do it continuously for a long time, what will happen to the error signal? Error here will go to 0. This shouldn't be surprising. This is how a working negative feedback system will operate. A working negative feedback loop will try to make sure that the feedback signal tracks the input signal, so that over the long run, the error is the signal that is processed by the comparator. The error signal goes to 0. Okay, great. So this is how a normal SAR works. Now let us consider what will happen if we have a mismatch in the capacitors. Okay. So for that, let's take a simple 3-bit case. I have, let us say, 4C, 2C, and this is always connected to Vref. Now let us say this is controlled by a bit B3, B2, B1. Now remember that this capacitor is connected to ground depending on this bit. This is connected to ground based on this, and so on. Okay. Now let us say I find that this bit is 1. So let's say I start with this, right? Let's say I make this guy to be 1. I connect this to ground, remaining is all at Vref. So what will be the reference voltage I am comparing my input with? Vref by 2, right? Remember that in the logic that we have seen, the reference voltage with which I am comparing the input is basically the total capacitance connected to ground by the total capacitor. Okay. So here I have a case where the MSB is toggling it, so it's Vref by 2. Now similarly, let us say this bit is 1. Let's say this is 0, 0, 1. Then what I'll do? I'll connect these guys to V. Now what is the voltage I'm comparing the input with? Vref by? No. The logic is right. I mean, remember that we had already put in an initial condition and all. So the deal is this: the capacitor connected to ground by the total capacitance times Vref. That is the reference voltage I am comparing my input with. That is Vref by 8 here, right? So essentially, if I were to sketch the characteristics of this guy, where the input is the digital bits I feed, output is the let's say the feedback voltage here. This is basically the reference voltage. If the signal is 0, 0, 1, I compare with Vref by 8. If it is 0, 1, 0, I will be connecting this guy to ground. This will be at Vref to Vref by 8, and then it's going to be increasing like this. So if you plot a characteristic, you'll get a nice straight line. Is that okay? So now let's assume that there is mismatch in the capacitors, which means this is going to be some delta C1, this is plus some delta C2. Now what will happen? I mean, loosely speaking, what will happen to the characteristics? It will be all over the place, so it will be some hugely nonlinear characteristic, right? So now you see that the DAC characteristic is no longer linear, it is terribly nonlinear the moment you have mismatch. And that's what we also hypothesized, right? If you have mismatches in the capacitors, we'll have nonlinearity, right? So if I were to incorporate this nonlinearity in the model we have, what I'll do is this. So I'll introduce a nonlinearity here. Okay, that's fine. So now if you see, my negative feedback loop is a poor thing. It doesn't know anything. All it can do is it will try to make the feedback signal equal to my input signal. So now what will be, which two signals will be equal now? The feedback signal will be equal to the input signal. The feedback signal is, let us say, f of d out, right? Now what will be equal is f of d out. That is what the negative feedback loop will do. It will just try to make sure that the feedback signal tracks the input signal so that the error signal which is processed by the comparator is 0. That is the whole point of, that's how a negative feedback loop operates. Is that okay? So now what we have is this, let me put it to next page. F of d out is d in. So which means d out is, what is d out? F inverse of V in. And as you expect, we have nonlinearity. The digital data, if you process it as such, it is a nonlinear function of the input. Now what should I do to my output so that I get V in? No, from this, right? I know d out is F inverse of V in. If I want to get only V in, what should I do? I should pass the output through a nonlinearity which is F. That's basically this, right? So I take my d out, do a processing on this so that it implements this nonlinearity, then I'll cancel this nonlinearity. So what we have to do is this. So let us say it's a 3-bit DAC, right? So we'll get B3, B2, B1. Nominally we reconstruct the output as this 4B3 plus 2B2 plus B1. This is a linear reconstruction. Now we no longer should be doing this. We should be doing it in a nonlinear fashion, and that simply boils down to the fact that I'll have to have some K3 times B3. Yeah, the nonlinearity here is coming because if you think about it, the capacitors are all, let us say this is, instead of 4C, it is some 4 point something times C. This is 2 point something times C. So instead of reconstructing as 4 plus 2 plus 1, you should be reconstructing like this. That's all. Because the negative feedback loop is doing the same, right? If you basically can get this signal, that will exactly match input. But at the output, we are only taking D out. So if you can do the same function that is being done in the DAC, you will be able to get back the same signal. Is that okay? So this is how we'll have to do, and of course it's much easier to say than to implement, but it is doable. So bottom line, this capacitor mismatch will introduce severe nonlinearity, and if you want to realize higher resolution, you'll have to tackle this capacitor mismatch, which usually is done in the digital domain, right? Cool. So now let's discuss the last issue I want to talk. Now remember that in the SAR ADC we are going to sample the input onto the entire capacitor I'm going to have, CS. And as we discussed just now, in practice, this sampling capacitor will not be determined by KT by C noise. It will be limited severely by the minimum capacitance needed for getting some particular matching. So this will be much higher than what is required for KT by C noise. Okay. Now remember that this guy is going to be driven by some buffer. Why do I need a buffer? Why do I need this buffer to try the ADC? In general, why are you using buffers usually? It isolates, but yeah, the deal is, see, this could be, let's say you are trying to digitize some data, so the actual thing can be a sensor or some other source, right? you have to sense the voltage here without drawing any current, because the moment you draw any current from it, the voltage can get changed. So that's why you need to have a buffer. Okay. So now we know that this guy is going to have an on resistance. So let us say the capacitor is initially uncharged. You switch the turn the switch on. What will happen to the current? This is V in. At the instant of switching, what will happen to the current? It will jump to V in by R on, and then it will decay to 0 exponentially. We all are familiar with this. Now let us say I am trying to realize a ADC operating at a faster and faster speed. Then what can you say about the time available for sampling? It's going to be reduced. So which means what can you say about R on? R on will also be much smaller, right? So which means this current will be much higher. And remember, who is providing this current? Buffer has to provide the current for charging the capacitor, right? So the buffer has to provide this spiky current, and the spiky current is so high usually. So if the current provided by the buffer is so high, what can you say about the bias current in the buffer? It has to be much higher than that, right? And in addition, what will happen is this, right? See, we want to make sure that the buffer doesn't add any non-linearity by itself. You might have designed an ADC with very good linearity, but this buffer should not add its own non-linearity, right? And it turns out, without going into a lot of details, to get a good linearity out of this buffer, you have to have more and more power consumption. So in practice, what will happen is this: the buffer here will end up consuming significantly higher power than the SAR ADC itself. So in practice, it is not uncommon to see a case where the buffer power consumption is, say, 2 or 3 orders higher than the ADC power consumption itself. Okay. So this is a huge bottleneck in SAR, because by design SAR ADC itself is very compact, has all digital blocks, and consumes only very small amount of power. It can be few tens or few hundreds of microwatt at the max. But to design this buffer, you will end up burning tens of milliwatts of power. Okay. So this is a huge bottleneck. So this buffer power, and in particular buffer non-linearity, is a huge issue. So let's see if we can do something about it. And for that, I'll actually bring your attention to the negative feedback model that we had. Where did we have it? Yeah. Let me just copy this. Okay. So I'll not consider the capacitor mismatch, only one issue at a time. This is how SAR ADC operates. Now the issue is, I cannot feed the input directly, I need to have a buffer. Now the buffer is non-linear, right? So if this is V in, the actual signal fed here is non-linear function of V in. So which means my feedback signal will track the non-linearity, output is non-linear. So now let us see if we can do something about this. See, one thing is for sure, I have to use a buffer to feed the signal. Before reaching the comparator, the input has to be given through a buffer, and the buffer output is what should be given to the comparator, right? But if I add the buffer here directly, that's creating non-linearity. So is there some other place where I can add the buffer in this system so that I can avoid this?
Can copy this after that connection?
Right, makes sense. This is the suggestion. Sorry, let's put this. What's your concern? Here was what he suggested, right? So let's put it here. So now you see, V in, this buffer can add its own non-linearity, but the negative feedback loop doesn't care. All it knows is, you give me a signal, I'll make sure my output feedback signal tracks, and the input is also not given directly, we are buffering it, right? So this is one way in which you can do. and I mean this is quite recently done, and this technique is usually called buffer-embedded SAR. Now this at a block level, let's see how we can implement in circuit. There are a couple of ways in which you can do. I'll just show one variant. We take here. Yeah. See, in the practical SAR implementation, one difference from the way we have written the model is this, right? So let me. In the model, we have written as though the input is continuously getting sampled and compared with the feedback. But in a practical implementation, in a SAR, we first sample the input only once, and that is stored and then compared with successive reference voltages. That's what happens, right? And here, the way we have drawn the block diagram, what we are doing is the input is buffered. Similarly, the feedback signal, which is the reference signal, is also buffered by the same buffer. That's what is happening here. So when we are implementing it, this is what we have to take into account. Both my input and the reference voltage I am generating, both of them must be buffered by the same guy, right? So let's start with the sampling phase. We have to sample the input. So for that I am going to use a buffer. And initially let's assume the buffer is ideal. Then we'll introduce nonlinearity. So let us say I am putting it in a sampling capacitor. So this is V in, this is also V in. So the voltage across capacitor is, right? So now we have to generate the reference voltages. How did we generate reference voltages so far? We had the capacitive binary weighted capacitive structure and we switched the capacitors. Now one difference here in this and our previous implementations is, in our previous implementation, we had this binary weighted capacitive DAC. We sampled the input on the same capacitor, right? We had the capacitive array like this. We sampled the input on this guy and generated the reference in the same capacitor. That's what we are doing. But here, as you can see, we cannot do that because the input first has to be buffered, reference also has to be buffered, right? So I can't directly sample the input on this guy. I have to use a buffer, which I have done. Now similarly, the reference voltage I am generating, that also has to be buffered. Okay. So the only way I can do this is to have separate capacitor for sampling the input and a separate capacitor for generating the reference. Is that okay? Because here you see the reference voltage also has to be buffered, right?
Yes.
So using a capacitive array like this, I can generate reference voltage which I will buffer. But I cannot go and sample the input on this, right? Because the input also has to be buffered. The only way to achieve this is to have separate capacitor for storing the input and for storing the reference, right? So in sampling phase we do this, and when we are actually doing the conversion, we have the capacitive array like this. So I mean, one capacitor is always connected to Vref and others are connected to Vref or ground. Now the rest is, I mean, the way we switch the capacitor is all going to be same. Earlier what we did, we put an initial voltage of V in minus Vref and then we switched capacitors. Now we don't have to do that. The input is separately sampled. So the initial condition you don't have to put. You can do the rest of the switching as usual. Okay, that's the only difference. So now this will generate the reference voltage. And what we have to do to the reference voltage? Should I feed the reference voltage directly or should I do something? I have to buffer it. I have to use the same buffer, right? So what I'll do is this. Same buffer. Now in principle I can give it to the comparator. What should be the input I should give to the comparator? I mean, I can't just give the reference, right? What should I give? I mean, I'll just say the, yeah, buffered reference. Let us say, what should the comparator compare? V in and this, right? So basically, let's say this. It can be V in minus VFB or sign doesn't matter, right? Now this is, let us say, the feedback voltage. That is the reference voltage. This is basically the same guy. Now this is the feedback voltage. I have to subtract the input. What should I do? You can use a capacitor charge to it, and you already have the sampling capacitor. You already sampled the input onto the previous capacitor, so use that guy. Now we can do. So this is how we can make this SAR. But now let us say what happens when we have nonlinearity, right? So this is now nonlinear.
That two different buffers?
Same buffer, right? That's the whole point.
Single buffer used at two places or two different?
No, one buffer, right? See, the point is we are not doing these two guys at the same time, isn't it? We are going to sample once. Use the same buffer for buffering this guy. Once.
When are you feeding
V in is here, right? That's what we have sampled the input here.
Okay, there are switches.
Is that okay? So now if the buffer is nonlinear, what will be the voltage sampled across the capacitor? It won't be V in, it will be a nonlinear function of V in. So this guy is also storing f of V in. Similarly, this is the feedback signal, the reference voltage. This will be the nonlinear function of the reference voltage. So what will be the signal that is fed to the comparator? And as you know, the negative feedback loop operates to make this error signal go to 0. So which means this will go to 0. So which means f of VFB is f of V in, which means the feedback signal will properly track the input. Okay. So this is really nice. Now you see that my buffer, even if it has a nonlinearity, at the output it doesn't come at all. Now it works on another level, which is the following. Now in our conventional SAR ADC implementation, the input was sampled onto the same capacitor as the capacitor we are using for generating reference voltage. And there we saw that for getting good matching between these capacitors, we need to use a minimum capacitor for the unit, which means the total capacitance we have in this array was much greater than what was required by KT by noise. Right? But now you see that the sampling capacitor is different from this guy. Right? So now the sampling capacitor here, CS, can be sized only based on KT by noise. Right? Now we have to ensure matching only for these guys, and for these guys you use a large capacitor. Now why is this good? Because the capacitor that the buffer is driving is now really small. In the earlier implementation, the buffer would have been driving this entire guy completely, which means this capacitor is so large, buffer has to consume more power to maintain linearity. Now the capacitance the buffer is driving can be reduced, which means to maintain the same linearity, buffer can consume lower power. On top of it, even if the buffer is non-linear, it is okay. So there is no reason to go and burn more and more power to make it linear. We can reduce the power consumption in the buffer and make it non-linear, it is still okay. But in practice, do you think we'll be exactly able to cancel this, or do you foresee something? Obviously it will not exactly get cancelled, right? But where is the point here? Where is the catch? We are getting this guy VFB equal to V in only if these two guys are equal. So here I have assumed that the input sees some nonlinearity f, the feedback signal sees the same nonlinearity. But if you think about it, my input is a time varying signal, but my feedback is a reference voltage, it's a constant signal. So the behavior and the nonlinearity of the buffer, when it processes a time varying signal, will be different than the nonlinearity of it when it processes a constant signal, right? So this could be in practice some f hat. right? So finally, if you find it, it's going to be what, some f hat inverse of f of v. So we'll still have some residual nonlinearity, but it will be much better than like earlier case. And this technique was quite new. It's only 2019. You can share the reference if you want. And I mean, see, bottom line, in a SAR ADC, so this buffer design is a crucial thing, that is a actual bottleneck, because the SAR ADC itself will consume like negligible amount of power. The actual current will be burned in the buffer. So this is one of the burning issues when you integrate SAR in an overall system. I mean, if you design just the ADC alone, I can say that, hey, my ADC consumes picowatt of power, nanowatt of power. But when I'm going to use it in a bigger system, this is going to create a lot of issues. So this is one of the major challenges or design bottlenecks in a SAR, and people are still working on it. And as you can see, even the solution that we discussed are quite recent. And the second other main issue in a SAR is the capacitor matching. How you can match the capacitors well so that you can reduce the sampling capacitor you can have. So those two are the main stuff. So I think that covers what I wanted to discuss on SAR. So yeah, this topic.